Okay, so these are the review slides for exam 2 for organic 2 in the spring 2017. So this is going to be a lot of the dealing with infrared spectroscopy, UV spectroscopy, NMR, and mass spec. So these are the free answer parts. So one of the questions will be, like how many different signals would you expect in the in the hydrogen NMR and carbon NMR, for the following compounds. So here's our compound here, right? So for the hydrogen NMR, one of the things you may want to do is to go ahead and just draw in the hydrogens, okay, that you don't see in the skeletal structure, right? So there's 2 here, so this is CH2, this is a CH3, okay? So these guys here, this one, and this one, right? Those are all chemically they're all chemically different, so each one of these is going to give a different spectrum, right? We're not going to see hydrogens here, because anything from here, because there's no hydrogens there. With hydrogen NMR, you're just seeing, you're just checking out the hydrogens there. Now for this one, now for these two, it turns out that these are equivalent to each other, okay, and these are equivalent to each other. Because if you were to imagine that you were to hold these two fixed and then spin that ring around like a coin, stuff like that. So what you can do is you can flip that ring, right? Because you can get free rotation here. So these two hydrogens can be, you can flip this over and it would still be the same molecule. Same thing here. These two could flip back and forth, as you rotate, and they would be equivalent to each other. So you would have 1, 2, 3, 4, 5 hydrogen signals. Now with the carbon, right, again, you're going to get a signal for these distinct carbons here, but then you would also pick up these two as well, here, and they're distinct because this one has a methyl group hanging off of it, and this has an ethyl group hanging off of it. So each one of those is going to generate a signal. And then these two here, for the same reason why these two hydrogens are the same, these are chemically equivalent. This carbon here and this carbon here are going to be equivalent, and the same thing's going to happen with these guys, this carbon and that carbon. So you're going to have 1, 2, 3, 4, 5, 6, 7 signals in your carbon NMR. Okay, now for this one, right, I'm going to give you a pair of molecules, and I'm going to give you some IR spectrum. Now, in the instructions, I'm going to tell you that assume that the alkane carbon-carbon and the alkane carbon-hydrogen are also present. Okay, I don't like putting those in there because it can sometimes muck up the works. Okay, so the way that you can approach this is to come in here and just list what peaks you would expect, right? So both of these are going to have, the alkane, carbon-carbon, carbon-hydrogen. So both of these are going to have that. Pretty much all molecules are. Okay. Now this one, that's all it's got. It doesn't have any other functional group, so that's all it's going to have. But this one, right, we're going to have carbon-carbon bond for here. But remember, there are hydrogens coming off of here, so you would also see the hydrogen coming off of an alkene, and that's going to give a very distinct signal, something like that. So this one here, you would just hit the carbon, just the alkane signals. But here, you look on this chart, it doesn't match up. So for here, the carbon-carbon double bond, right? So again, you're going to have this chart on the test. This is going to be 1620 to 1680, right? And then this one here is going to be between 3000 and 3100. Okay, both of these are going to fall right into this range here. Okay, so this is going to be the molecule represented by this IR spectrum. Okay, now for this one, same thing, right? So they're both going to have carbon-carbon, carbon-hydrogen, alkane. This one's going to have carbon-carbon, carbon-hydrogen, alkane, right? But this one here, right, you're going to have this carbon-carbon triple bond, okay, plus the CH bond coming off of that alkyne, right? So the carbon-carbon, that's the alkyne, right? So that's 2100 to 2260, right? And then this one here, the CH coming off an alkyne is right at 3300. Okay, this one here, you're going to have the nitrile, group here. Okay, you see here, this is also 2210 to 2260. Okay, so this one actually goes both here and here. Okay, so which one do we pick? Well, the thing is, if we had this molecule, we would also need to have this peak here. We don't have that. Okay, so it can't be this molecule, so it has to be that one. So you remember with IR, it's what's there and what's not there. Okay, so if it's not there, there's a reason. So it has to be that one. Okay. Now for here, we're going to be using Beer's law. Okay, so when you're talking about UV absorption, stuff like that. So absorption is equal to your molar absorptivity, right? Or your extinction coefficient, either one, times the path length times the concentration. Okay. So here, so you have a reading, right? So 0.025, right? Your absorption. Okay. Your molar absorptivity, right? So it's 6,300 per molar per centimeter, right? Your path length, right? Using a standard 1 centimeter cuvette, so 1 centimeter. Okay, and then you don't know C. Well, the nice thing is the centimeters cancel out, come out. So we're going to divide both sides by 6,300 per molar. Right? So concentration ends up being 0.025, right? Divided by 6,300, right? M being the if you divide something, it's going to end up flipping into the numerator. So this ends up being 4.0 times 10 to the minus 6 molar, or if you want to be really fancy, you can say 0.0 micromolar. Okay, so micro means times 10 to the minus 6. So I'll take either one, but if you need it, there you go. So yeah, so usually what you're given is you're giving these, you have 4 variables, right? You usually get 3 of them, and you got to find the 4th. Now, if you will notice down here, at no point did we use this, the wavelength that we observed. That doesn't matter. Okay, so you can just cross it out to ignore it and stuff like that. It's usually put in there just to fool. I mean, it's important information if you're doing the experiment, but for doing the calculation, you don't need it. Stuff like that. So just avoid it. Okay, so here we go. So for this one, okay, so we're given a mass and an IR predict the structure. Okay, so like that. So usually what you want to do is you want to start with the IR information. Okay, so you look at your chart. Okay, so you look here and you figure out that this is right around 1700 is usually the C double bond O here. So 6900. So it could either be an aldehyde or ketone, or it could be an amide. Okay, the other ones aren't possible, but we can rule out the amide. Okay, because this number is even. Remember the nitrogen rule. If you have an odd number of nitrogens, you're going to have an odd M plus value. Since this is even, we can rule that amide out. So it's either going to be an aldehyde or ketone. So what we know is that there's going to be a C double bond O as part of that molecule. Okay, so like that. So that means that the mass, okay, M plus is equal to it's the total number of carbons, hydrogens, and oxygens. Okay, 58. Now, especially since this is so low, you can assume we really only have one ketone group. Okay, so that means that H, right? So with the mass, so you know that there's going to be one oxygen here. So, the 16, right? So 58. So that means the carbons and hydrogens are going to end up being a mass of 42 AMU. Okay. Now the way that you end up doing this is you say, okay, how many carbons and hydrogens? So if we had 2 carbons, okay, what's the maximum number of hydrogens we can have if we have 2? Turns out there's a little equation, 2n plus 2. Okay, so twice the number of carbons plus 2, right? So we 4 plus 6. Okay, so C4H6. That's the maximum number, maximum weight that we can have with just a straight hydrocarbon with 2 carbons. So that would be 2 times 12, right? You have 2 carbons, each of them worth 12, and 6 hydrogens, each of those are worth 1, so it's 24 plus 6, right? So this would be 30. Okay, there's no way that we can pack more hydrogens onto this to get up to the 42, okay, because we're at our max. But if we have, let's try 3 carbons, right? So maximum number of hydrogens, right? That would be 8. Okay, so it would be C3H8, so 3 times 12 plus 8 times 1, right? So that ends up being 44. Well, we're just above this, so the maximum we can have is 8 hydrogens. But if we subtract 2 away from here, 2 hydrogens, okay, that ends up being C3H6. Okay, so that ends up being, if you were to do that, that would be 42 AMU. So therefore, our final formula is C3H6O. That's the final formula. Okay, so but I didn't ask you what the formula is. I said draw a structure. Okay, so the first thing you got to do is to do a DOU calculation. Okay, so 2 times the number of carbons, right? So it would be 3 plus 2 plus the number of nitrogens. We don't have any nitrogens. Minus the number of halides, no halides. Minus the number of hydrogens, right? I'm going to get 6. All that divided by 2. So like that. So 6. So remember, I'm going to give you that formula. So like that on the test. So it's on the equation sheet. So like that. So this is 6, 8. So it's 8 minus 6, all divided by 2. So 2. So our DOU is 1. So remember, that's rings plus pi bonds. Okay, but we know it's going to be a pi bond, right? Why? Because we have to have this for. So now, if you do the DOU, go back and take a look at your IR information, right? We know we have a ketone in there, so it has to have a C double bond O. So that's your pi bond. So we don't have any rings, but we have a pi bond as a C double bond O. So therefore, right? So we have 3 carbons, right? So it's either going to be have the C double bond O there and then fill in, so you have the aldehyde, or it's going to be your 3 carbons, or it's going to be like this, which is acetone. So it's either going to be one of those 2. Okay, these satisfy that information there. Okay, we can't get any closer than that. Okay, so there you go. Okay, so for here, okay, so for carbon NMR, okay, so first thing to do with all these problems, right, is get a DOU. So DOU, right, so 2 times 5 plus 2, no nitrogens, no halides, but 10 hydrogens, right, so 2. So if you do that, so 12 minus 10, 2, so that ends up being 1. So you know you either have a ring or a pi bond. Okay. So about that. So next up, so that check your depths. So about that. So the depth. So the depth 90. This is going to show all of your CHs. Okay. So here we have. So this one here is going to be a CH. Okay. Your 135. This positive is going to be. It shows your CHs or CH3s. Okay. We already know that this is a CH. Okay. So that means we don't have any CH3s in here. Here, the negative depth 135 shows the CH2. So that means all of these guys, each one of these is a CH2. Okay, so it is. So we've assigned what that is. Now at this point, it's usually good to do a check to see what can we account for. Right. So we have 1, 2, 3. We have 4 CH2s and a CH. Okay. So 1, 2, 3, 4, 5. Right. So we have C5. 2, 4, 6, 8, H9. Okay, that's what we have accounted for. Our molecule is C5H10O, right? So if we subtract out the C5H9 that we know about from the depths, what are we left with? Well, no more carbons, but we have an H and an O. Ooh, that's looking good, because what that might mean is we have an OH that we haven't accounted for yet. Okay, so you can always figure out what you've accounted for, right? So like that. So what we haven't so far is the OH. So that's probably going to be an OH group that we need to worry about. So okay, so next look at the chemical shifts. Okay, so here we look at the carbon NMR shifts, right? Again, I'm going to give you this chart. So these guys here, the 30 to 30s. So for that just looks like, so these down here in this range. So these are going to be just regular alkanes. Okay, this one here, the 60, that's pretty high. Okay, and it falls right into the range of having an alcohol, a carbon with something like an alcohol on it, right? So we still have that OH right with a carbon, right? So it's falling right into that range. It could, could be pretty close to the triple bond, but we only have one DOU, stuff like that. So it's most likely this is going to be with the alcohol on it. Now these guys being so high, that falls into the range of the C of carbon-carbon bonds, right? So that's about 100 to 150. So like that, both of these are in here. But so this molecule here is going to have a CH2 on one side of that double bond and a CH on the other. Okay. So the nice thing about that is that one, we can take it. We know that that means that this is going to be a pi bond. We've taken that into account. Okay, so we figured it out that it's not a ring, it's going to be this carbon-carbon bond. But the other thing is the fact that, see here, if you draw this out, okay, this part here has to be at the end, because there's no way, this carbon already has its 4 bonds, there's no way that you can extend this away. So really this has to be at the end of the chain. Okay, and so the rest of these have to be CH2s, right? So we've taken this one, and the rest of these are CH2, 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 CH2. Okay, so they have to be that in the string, right? So with that, they're not equivalent to each other because they're each individual. They're all CH2s, and it can't be a ring. So with that, okay, so this one, this has all its 4 bonds. So does this one. This one has its 4 bonds. This one has its 4 bonds, right? But this one only has 3. So for that, but there's still an OH we have to take into account. So the only place that it can go is there. So there's your structure. So there's only one way that we can put this thing together that it makes sense. And so there's our structure there. So the way that I usually do this is one, do DOU. Okay. Next, go in and do your depths. So with that, to see if you have the CH, CH2, CH3. If it doesn't, I forgot to mention, if it doesn't appear in these, okay, then it's just a carbon without any hydrogens on it. Okay. Next up, so you can sign those. Next, I usually do see what if there's anything you can't account for. So we add up what we know and subtract it from our formula. So when we subtracted it, right, we had an OH behind. So we have to take that into account. So with that, and then you can come in and look at your chemical shifts and see what that tells you, right? So these we said they're just regular alkanes, right? So with that, so this one here, it makes sense that the chemical shift is so high that it's probably has an OH on it. And here these are in the fingerprint region for being part of an alkene. So with that, so then you can assemble. With that. So if you get stuck on this one thing you may want to do is to just put the molecule together. Just start putting it together. Put some things on a paper, because then you can sometimes see, this part needs to make sense. I can't have a CH2 at the end, stuff like that, because there's not a 4th bond or something like that. You can go ahead and start throwing this thing together, and sometimes it'll help you click, stuff like that. So, okay, like that. So,
I'm gonna come in tomorrow.
Okay. So last part. So this is a hydrogen NMR problem. Okay, stuff like that. So for here, you're going to need these chemical shifts up here. So again, we're going to do the same thing. So the first thing is to do a DOU. So with that, 2 times the number of 10 plus 2. No nitrogens, no halides, but there are 14 hydrogens, right? So 2. So this ends up being 10. So it's 22 minus 14, 2. So that equals 4. Now, a good ballpark, a good rule of thumb is that if it's 4 or more, you're probably going to have a benzene, right? Because the benzene, right? So it looks like this, right? So with that, so you get 1 degree of accession for the ring, and then you have the 3 double bonds, stuff like that. So if you have 4 or more, there's a good chance that you have a benzene in here. So just keep that in mind. Okay, so here, usually what I do is I'll start with the integrations. Okay, so this one here, it's a CH3, right? So you can start with that. Now, the triplet, remember this is the n plus 1. Okay, so what plus 1 equals 3 to the triplet is 3, right? So with that, so this must be next to a CH2 group. Okay, This one right here, okay, it's a CH2, but notice I have a triplet of quartets. That means on one side would have, just like this one here, right? So you'd have CH2 because it's 2 plus 1, a triplet. So on one side you're going to have a CH2, okay. On the other, right, you have something that makes a quartet, and so that means it has to have 3, so CH3 group, okay. Here, right, you have a CH3 group, so you just have a methyl, right? But it doesn't have a singlet, right? So what plus 1 equals 1, right? Well, then you can't have any neighbors, right? So C. So here again you have a CH2, right? Triplet, so it would be a right. So CH2. Here you have 2 hydrogens, right? Right next to a doublet, so CH. Okay. Here again you have a CH2, 2 equivalent hydrogens, right next to a CH. Okay, so we sort of figured out where the neighborhoods for these. We have 1, 2, 3, 4, 5, 6 signals. We have 10 carbons, so that when they have some equivalencies and things like that. But also for that. Okay, so what do our chemical shifts tell us? Well, these two guys, okay, so right around 1, so these two are probably getting pretty close to being, right, so these are probably just regular alkane peaks, okay. This one here at 2.5, okay, so remember when we were talking about the fact that we have a benzene, well that would make sense if it's next to a benzene here. Okay, actually both of these look like they're probably next to a benzene, right? Because they're both right around 2.5. Okay, so about that. So and then these guys here, these are going to be on the benzene itself. Okay, because that is a big fingerprint region right around 7. It's going to be on the benzene itself. Okay, so about that. So here we go. So how do we get it so that we have benzene? We have 4. So about that. So we have 4 hydrogens on our benzene, right? So 2 from here, 2 from here, right? So that means we have 4 hydrogens on our benzene. But how are they arranged? Well, they're arranged so that 2 of them are equivalent and then the other 2 are equivalent. So the only way that we can do that is like this. Okay, so these 2 are going to be equivalent, right? And then these 2 are going to be equivalent. Now, what's happening is the reason why these are doublets is this one has one neighbor, so it's a doublet. This one has a neighbor, so it's a doublet. Okay, so it's effectively this is kind of weird, but essentially what's happening is these 2 are basically aligning and they're sitting on top of each other. So if you see this two sets of doublets in your benzene rings, it's almost always going to be like this. Okay, in this pair position, and then you've got a group coming off of here and a group coming off of here. Okay, because these 2 hydrogens are equivalent, these 2 hydrogens are equivalent. Okay, so for here, right, we said that these 2 are going to be next to the benzene, right? So one of these is going to be a methyl group, so let's put it down here. Okay, and the other one is going to be a CH2. Okay, so this is done, right? So we have a methyl group down here. Doesn't matter which side you put those on, right? They're just going to be on opposite sides. These are the only 2 places you can put them, because these hydrogens are filling out the other 4 spots. Okay, so here we're done. We're done with this one, right? We're done with these 2. We're done with this one. Okay, but you notice how it goes CH2, CH2, CH3, right? Well, here's a CH3 and CH2, so that's probably this part here. And down here, where is this? Oh, this one here, right? Now it's a CH2, CH2, so that's probably this part here. So what's happening is we have CH2, CH2, CH3. Like that. So here's our structure. Okay, so what do we have? Well, we have this. Well, we talked about how you get these 2 doublets here. We have a CH3. Okay, so we have a CH3 with no neighbors, right? The neighbor would have to be here, right? It's next to a benzene, right? So it's shifting it here, but it needs to be a 3 hydrogen singlet. Okay, this one here, if we had hydrogens here, it would get split, but it doesn't. So this one doesn't split. But here we have a 2 hydrogen triplet, right? A CH2 next to a CH2. Okay, now this guy happens because the chemical shift is so high, it's next to this benzene. And then here, right, we have a CH2, but on one side, right, we have a CH2 because of that triplet, and a quartet, which means on the other side we have a CH3. Okay, and then here we have a CH3, right here, just part of an alkane, right? So but it's next to, it's being split into a triplet, so that means the other one has to be a CH2. So all of these make sense. So here's your structure. Okay, so how do we do this? Okay, first thing to do is do the DOU check, and this sort of helps you sort of good information. It's a really easy information to have. It's worth a point, right? So go ahead and do that. Next up, I usually check the integrations first. So we have CH3, CH2, CH3, CH2, CH2, CH2. Okay, then do the splitting pattern, so you know what's around the environment for each one of these two, and then you check the chemical shifts. Look at your chart. Look what the chemical shifts are telling you, and then from here you can start putting the molecule together in such a way to rationalize how these things are going. So, okay, good luck.